Thank you, thank you. Hey, everyone. So let's talk about Houdini. But before we get started, a couple quick things. First, I am Snugug on the internet. But also, I have actually an interactive introduction to Houdini that you can play with in your browser right now, houdini.glitch.me. It's probably a better resource after this talk than the slides, but feel free to play with it either way. So let's get started. First question, what is Houdini? It's a pretty good question. It's not a magician. Houdini is actually a CSS task force, and the objective of the CSS tag Houdini Task Force is to jointly develop features that explain the magic of styling and layout on the web. Practically, though, what does that mean? Well, it means actually extending CSS via JavaScript so that authors no longer need to wait years for standards bodies to actually do something and get new things shipped to browsers. But wait, you might say, can't we do this already? Well, not quite. It's not currently possible to extend CSS via JavaScript. It's only possible to write JavaScript that can mimic CSS using existing CSS properties. Actually polyfilling CSS or introducing new features like CSS Grid to browsers that don't have them is hard to impossible to do, doubly so if you want to do it in a way that's not terrible for your user's performance. Houdini will let authors actually tap into the CSS engine, finally allowing them to extend CSS at native CSS engine speeds. The way that I like to think about it is much like service workers are a low-level JavaScript API for the browser's cache, Houdini introduces low-level JavaScript APIs for the browser's render engines. And that's pretty cool. So the question I always get is, can we use Houdini? Absolutely not. You cannot use it today. There are some implementations that are in production, but no, you can't. So a word of warning. All of this work is kind of early days. There aren't really any compatible implementations yet. I've been following this and giving talks on this for about a year, and all of my updates, or all of my talks have had API incompatible changes every single time I give them. There is going to be an API incompatible change happening sometime this week to one of the APIs. So terms and conditions imply your mileage may vary, not redeemable for cash. You've been warned that some of this is a little unstable. But it's cool, so we're going to talk about it anyway. First up, and kind of the building, one of the two core building blocks of the Houdini APIs are things called worklets. So worklets are extension points for render engines. They're like web workers, but much smaller in scope, can be parallelized, live on multiple threads, and most importantly, we don't call them. The render engines call them. So we just kind of set up stuff for the render engines to call. They look a little bit like this. We have a demo worklet sitting on window, and then we add a module, which is a path to the actual worklet script that we have. This loading is all promises, so we can promise all it and then off of the loading of all of them or await off of them, so we can take actions after we've guaranteed that our worklets have loaded. All worklets kind of have a similar structure. They have a function that's registered in whatever the worklet name is. They have a string, that's the name that we're going to call that worklet. And then they have a class, and that class all have some sort of process function on it. It'll depend on what worklet, with some sort of arguments, and that process function is the thing that our render engine is going to call. The worklet lifecycle looks a little bit something like this. We have our render engine, our browser. It's going to spin up our main thread, and it's going to spin up a handful of worklet processes. From there, our main thread's going to call our browser JavaScript. Our browser JavaScript is going to use worklet.addModule, and it's going to grab a worklet. From there, that worklet is going to be loaded into two or more worklet threads. Worklet threads can either be parallel threads to the main thread, or the main thread itself, kind of depending upon how it gets loaded and implemented by the browser. But the key here is worklets don't have scope. You can't guarantee that a worklet will be called within the same scope every time. And they're in multiple threads so that they can be parallelized and kind of run at those native speeds. When something needs to get used, it gets used by the render engine calling it. So it'll call that process function. Worklets, they really provide this underlying foundation for which all of Houdini is based. And they're really kind of the secret sauce that let Houdini do its work at render engine speeds. The next big thing we get is the typed OM. So the typed OM is a structure that actually provides CSS values that we can use above and beyond just strings that we have today. It actually provides this new superclass CSS style value and a bunch of subclasses, like keyword value, position, transforms, units, and math. And all of these together give us an actual structured way of thinking about and dealing with and working with our CSS units, again, above and beyond just strings that we can do today. So as an example, if we've got background position that's center, bottom, 10 pixels, if we grabbed its typed OM, which is its computed style map, then we can get the background position's X value. And then that is actually an object that is a value of 50 and a unit of percentage, because we are centering it 50%. And the Y position is a CSS math sum that has an operator of sum adding together with an array of values, -10 with a unit of pixels, that's that 10 pixels up from the bottom, and 100%, 100 value unit percentage, which is that bottom bit all the way to the bottom. So we can actually start to performantly manipulate these things. The typed OM is really what's going to provide the glue to connect our CSS and our worklets together. So you might say, what can I do with these two things now that we have worklets and the typed OM? Well, the answer is you can do some pretty rad stuff. So next bit, the cool custom stuff. Please let me introduce you to window.css and all of the fun things that hang off of it. So the first really awesome thing we get with window.css and the typed OM are custom properties. Custom properties really let us make our snozberries taste like snozberries. So what's the current situation with CSS variables or CSS custom properties? Well, we have something like my color green, and then later on we set it to a URL and try and use it as a color. And that doesn't work, because a URL isn't a color. But then we can use window.css.register property, and we can tell our browser that my color is a color. Now it'll know it's a color. It'll disregard things that aren't colors. In fact, we can go a little bit further than this if we want to. We can decide whether or not that property inherits up and down the DOM. We can assign it an initial value. In addition to color, we can actually have lots of different syntaxes for it as well. A length syntax, a number, a percentage, URLs, integers, angles. Basically, anything that we would want to have as a discrete type of unit, we can assign as part of our custom properties. Now, it also allows for combiners, so we don't need just one. We can have a single unit. We can take a list of units with the plus. We can have ORs, which is the bars, so we can have ORs of different types, like image or URL. We could even have ORs of different idents, like big, bigger, and all caps bigger. And all of these are considered different valid values for our custom property. With this, it opens up the possibility for the browser to actually start working with our custom properties in a way that it can't today. So there is some live coding, but don't be afraid. I've tested this a lot. The current situation today is we've got this unregistered property, and if I hover over it, my gradient just kind of pops into place, because you can't animate gradients. But if we have a registered property, and we animate or transition the registered property, then when I hover over, it transitions Ooh. And we can even do things to validate that. So if we did URL foo, that URL foo isn't a valid color. And because it's not a valid color, it defaults to our default value, which is purple. If I change this to red, it'll transition. If I change this to blue, it'll transition from red to blue. So I don't need to do all these hacks to get gradients to transition. I can now do it because the browser understands what the custom property is meant to be. So the next cool thing is the Paint API. Every day is a good day when you paint. Really, I just like Bob Ross. So, question, have you ever wanted to use canvas as a background, a mask, or a border in CSS? And the answer for most of you is probably no, and I understand that, but I promise it's really cool. Because with Paint API, we can do that with the styling and flexibility of an element and the scalability of an SVG. The Paint API combines these all together into this really great way to extend our creative possibilities with CSS. So the Paint worklet looks a little bit something like this. We have static input properties and static arguments. The input properties are what's actually going to be read in from the DOM, the properties that are going to be passed. Input arguments, there is a new Paint function where we can pass arguments in. Whether or not alpha is allowed, this doesn't work so well, so don't worry about it. And then the Paint function itself, this is this worklet's process function. It takes in the drawing context, the size of the elements, the properties that are input, and the arguments that are input. So let's kind of build a basic one, a circle. Just paint a big circle inside of our element. So we're going to take in the property circle color. We're going to grab the circle color. That is a typed OM color. We're going to find the height and the width and divide it by 2. We are going to find the center. We're going to figure out the radius. And we're going to use the drawing context to draw, just like you would in Canvas. And the net result that you get after you've imported it is you get a green circle in your background. And we can change it with CSS to any color we want. And that's kind of great. But there are other really interesting things that you can do with the Paint API, like creating your own custom border images. So if anyone's needed to make tabs with those cute little rounded corners at the end, that's really, really hard to do in a way that scales, in a way that's kind of flexible. But with the Paint API, we can actually do that pretty straightforward. A little worklet to draw these with arguments for whether you want left, right, or both. And then we read in background color. So background color, I want to change from orange to pink. And now my tab, if you can see the little tiny curls, are pink because I'm drawing it using the Paint API, reading in that standard CSS property. This allows me to be really flexible in my design systems without having to build these sort of complicated hacks. We can even do fun things like generative art in CSS, where we can take our background and we can actually create backgrounds on the fly using generative art techniques. And when you combine CSS Paint with changing of custom properties with JavaScript, you can do things like have an animated background on elements or on click. So from here on out, things get a little bit fuzzy. The next two APIs that I'm going to show you are under active development, whereas Paint and everything else is kind of mostly stable. So the first one is the animation API. Because, yo, I heard you like parallax. So what the animation API will let you do is listen for user events, like scroll events, and style elements based on that user input. But most importantly, do it all off the main thread. It's what's actually going to make parallax performant. So the animation worklet looks a little bit something like this. You've got a constructor that you can take options in, and you have this animate process that takes the current time, which is the time in the timeline. We're going to be working heavily with the animation API. And effects, which is an array of keyframe effects from the animation API that you want to actually work on. So we're going to build the Twitter header right now, where the header fades in and the avatar kind of scoots up and transforms down. So we have our main body, which is our scrolling container. Where our scroll bar is our scroll position. Our header is going to start at opacity 0 and go to opacity 0.8, I think. And then our avatar is going to start large and scale down. That's the effect that we're going for. So with that, we'll register an animator, which is Twitter header, which has a constructor where we're just going to build a cubic Bezier function for easing. We're going to have this internal function called clamp, which is kind of a way to make sure that we don't get larger or smaller than certain values. And for animate, what we're going to do is we're going to set the local time, so the point in our animation, based on the time that's being passed in, based on that scroll position. Now, this is where being able to load in our worklets becomes handy. So we can await our animation to load, and then we create a new worklet animation once our animation API, or sorry, once our worklet is loaded. We're going to use the Twitter handle, or Twitter header, and we've got an array of keyframe animations. These are going to become those effects. The avatar is going to go from scale 1 to scale 0.5, and its duration is going to be 1, and we're going to go through it once. Our header is going to be opacity 0 to 0.8, same thing. And then we're going to use for our timeline a scrolling timeline. So we're going to use our scrolling container, our body, as the thing we're listening for scroll, give it a time range, tell it where it starts scrolling, tell it where we want to stop scrolling. And finally, we're going to play it. Building this all together gives our render engine, gives our browser all the information it needs to actually run this off the main thread for us. So while we're setting this up in our main thread, it's not actually running in our main thread. So as we go, again, our header is keyframe effect child 0, and our 1, and then our avatar is 0. And the effect looks something like this. As we scroll, these items pop into place. So this is a little bit more complex, but these items pop into place as we scroll, and it's all based on scroll position done off of our main thread. We can even do just straight parallax with different items at different rates. And then finally, we have the layout API. The layout API is going to let you do Tetris with your websites. Now, I will say that the layout API is kind of really big. What the layout API does in its spec is it literally explains how the layout algorithms work on the web. Because this will and does let you make your own display properties. It'll let you do things like polyfill that new awesome spec layout you love. In fact, someone has polyfilled subgrid for CSS grids using the layout API today. And because everyone likes a good masonry layout, I'm going to show you how you can do it without a performance hit in less than 50 lines of code without any external dependencies, all through the magic of the layout API. So in order to understand the layout API, we unfortunately need to go through some terminology, but at the other end of this, you'll understand how browsers think about layout. So at the big thing, we've got our parent layout. This is the thing that actually has, the element that actually has the display property on it. Inside that parent layout, there are two things. It's layout edges, that is your border, your padding, your scroll bars. And it has layout constraints, which is the inline and block with text perpendicular to text, sizes that are available to put content into after you've removed layout edges from the size of the element. Each item being laid out is a current layout, and that current layout creates a layout child. That layout child is the actual layout being worked on, child layout is the actual layout being worked on, which has a layout child. The terminology is confusing even for me. I am sorry. I didn't write the terminology. It just is what it is. And those layout children each have fragments, which are the things that we can actually manipulate to lay something out on our page. So looking into layout child has a style map, which is the typed OM style map of all of its properties. And it also has the ability to run a function layout next fragment, which will actually generate a fragment from that layout child. A fragment has that layout child's inline size, so size in the direction of text, and block size, the size in the direction perpendicular to text, as well as block offset and inline offset. Now, when we go to lay stuff out, we change the block offset or the inline offset, and that's how we position things around. Layout edges has inline and block sizing for padding, borders, and scroll bars, and this helps us understand our constraints and where to put everything. So let's take a look. We have a worklet for layout API, which takes input properties, which are things like grid gap for CSS grid would be an input property for the parent layout. We have things like child input properties, which are things that we want to understand about the actual child being laid out, so something like align self or grid column. And we have some layout options which will determine how the layout actually behaves. So does it transform it into blocks like flexbox or not? Then we have two functions that today are generators and will be changing to promises soon. One is intrinsic sizing, which is how we actually calculate the min and max size for a block. And we have layout, which takes in the children, the edges, the constraints, the style map, and break token, which is mostly used for printing. We're not going to use it much today. So let's dive into what a block layout is. So basically, all blocks at their right size, centered, one on top of each other. So for intrinsic sizing, like I said, intrinsic sizing is about understanding the smallest a block can be without overflowing content, and the largest a block can be without having extra space. So the intrinsic size function determines that, and then we return max content size and min content size, and that will be used by the browser to figure out how big to actually make each one of our blocks. We then go on to the layout function, and the layout function, intrinsic sizing, I still really don't understand, but the layout function is actually not terrible to understand once you have that terminology in your head. So the first two things we do is we figure out the available inline size and the available block size by grabbing those from our constraints. And then we're going to build an object off of that. Next, we're going to generate fragments for each of our children by running over them and grabbing their layout next fragment from those constraints that we have available. Once we have all those fragments, we can then position them. And this actually is pretty easy. We start with 0, we start at the top, and then we loop over each one of our fragments, and we position it either in its block coordinate or its inline coordinate. We can position both. In this case, our block offset is just where we started from, and our inline offset is either going to be our inline size or the actual, or it's our inline size minus the fragment size divided by 2, so we're centering that block in our area. Then we're adding to our block offset the fragment's block size and the gap value that we have, because we're going to have a gap in between each one of these. But it's basically inline size where we want to position it x and y coordinates. And then once we're done with that, we return our child fragments, and we return that new block size, and that's going to create our new block size for our element. And it looks like this. It looks like a bunch of blocks sitting right on top of each other, if it would scroll. And we can do things like changing our gap to 20 pixels. That's 230. That's 20 now. And it's all being done at render engine speed. And now, like I promised, we could do masonry in 50 lines of code without any dependencies by building something that looks for padding in columns and doing a little bit of math to figure out the block and the inline offset, which for us means that we can do things like padding 20, padding 30, columns 2, and we have this full masonry layout without any dependencies at render engine speed, done in a way that will scale for everything. And to me, that's kind of really badass. Cool. Didn't expect an applause break there. That's fine. Yeah. So I think that's really cool. And more importantly, with this stuff, I think the future is really bright for CSS. While we're still kind of early days with Houdini, things like the Paint API do have a polyfill that you can start using in production today. Layout and animation need to kind of settle down a little bit, but they're getting there. And we should really all get excited, because Houdini is really going to open up what we can do on the web, the creativity we can have, and vastly improve the performance of some of the things that we have to do with hacks today. So get ready to add some magic to your sites. Thank you.